please welcome Maya Burnahanparkar.
Of one of the most enigmatic phenomena in the universe, and that is the source of cosmic fast radio bursts. Now, you don't need to be a cosmologist to be fascinated by FRBs. A professor, in fact, at my own university, Harvard, Dr. Avi Loeb, who is the chair of the astronomy department, has proposed that these might even be evidence of a super intelligent, extragalactic alien species whose light sails are reflecting these super powerful signals back at us. I personally think this is a little unlikely, but it's a theory that's out there anyway. You see, FRBs are random millisecond duration bursts of energy that are over 500 million times more powerful than our sun, coming from an emission rate region no larger than a few hundred square kilometers. So imagine if you took our sun and you condensed it into a few hundred square kilometers and then got 499 million more of them. So it's crazy to think just how powerful these signals are. And it's the sheer power of these bursts that makes physicists so interested in them. Could this be the source of new uncharted territory in physics? Could we use FRBs as cosmological probes of the universe, just like we did for pulsars and supernovas? The possibilities are truly endless. And as a result, there's a lot of speculation as to what these things could possibly be. Of course, there's the aliens theory, but there are also many more, including the collision between very dense objects like the merging of black holes or neutron stars, magnetar hyperflares. In fact, there are more theories speculating as to what these could be than there are total event detections themselves. But we don't really know if any of these are actually right or even powerful enough to explain the phenomenon. And so understanding what fast radio bursts are and where they come from could lead to a fundamentally new branch of physics that we can't even presently begin to imagine. Okay, so a bit of a history lesson first. The first fast radio burst was discovered in 2007 at the Parkes Radio Telescope in Australia, and it looked something like that. So just to give you an idea of what this plot is showing, on the y-axis we have frequency, and on the x-axis we have time. And this is a plot of intensity, and so that little quadratic burst that you can see is the fast radio burst itself. So why does it look like that? Well, if you had taken a camera and put it at the source of the fast radio burst, it would have just looked like a vertical stripe, with all of the frequencies arriving at the same time. But because this burst had to travel from the host galaxy all the way to our galaxy, the signal interacted with little bits of stuff in space called the interstellar medium. And it just so happens that lower frequencies tend to interact more, slowing them down. And so that's why you get this quadratic pulse, where higher frequencies arrive first and lower frequencies arrive later. So what's interesting about this burst is the fact that anyone saw it in the first place. In astrophysics, we have something of a data problem, which means that we collect so much data that it's physically impossible for anyone to actually look through it all with their bare eyes. And so as a result, we use a lot of computers to do this for us instead. So the computers will look through the data, clean it, get rid of all the noise, and then search for signals. But the problem with that is that you need to know exactly what kind of signal that you're looking for. And of course, we were never expecting to find something like this in our data. So it's very lucky that one of Lorimer's graduate students just so happened to look at this data and actually find the burst itself. Okay, so since this burst was discovered, there was a mad hunt over the next few years to try to find more of these in archival data. And in 2010, the same telescope, Parkes, published a total of 16 similar pulses. These bursts were so powerful that for a while, astronomers thought that they must have been a local interference from a microwave oven. Fortunately for us, that hypothesis was only true in a very small subset of cases. What had happened was that some very impatient astronomers didn't let the microwave finish running before opening it. I know we've all done it before, causing microwaves to spill out and contaminate the data. But thankfully for us, that was only true in a very small subset of the cases. So we still had 13 bursts from this paper, and another burst from the very first paper, and a very big mystery. And over the next 7 years or so, on the order of 24 other events of these FRBs were discovered. But the discovery process, until very recently, has been quite slow and cumbersome. So, what's the problem? Well, fundamentally, it's data. Since these were first discovered, as I said, we only have 24 total event detections. But the reason for this isn't that these are very low-frequency events. sense. In fact, they're about to happen almost 1,000 times, or maybe even 10,000 times per day that we should be able to see on our Earth. The problem fundamentally comes down to the design of telescopes, and that's what I'm going to talk about for the next little while. In addition, we don't actually know where these signals are coming from. Given that we've only found the signals in archival data, we aren't able to do interferometry on the data in real time. So we know that the signals are roughly isotropic, which means they're coming from roughly all around the celestial sphere, but we don't really know much other than that. So the two facts that we have about fast radio bursts are that they're roughly isotropic and that they are extragalactic, so they're coming from outside of the galaxy. And we know that because of how curved these pulses are. But that's pretty much all we've got. All right, so we have two very closely related problems. Number one, a lack of data, and number two, we can't actually make good use of our data because we can't localize any of our data points. And so, as I said, this has to do with the design of our radio telescopes. And so a team of Canadian scientists aimed to actually solve this problem. And the way that we did it was by fundamentally redesigning the telescope. So to talk about our big redesign, I first need to talk about what the conventional design is. This is what a radio telescope normally looks like. It's a big dish, and then there's an antenna right in the center. And that allows you to get really good angular resolution, but only on a very small portion of the sky. Which means that in order to actually detect one of these events, your fast radio burst has to happen to pass through the beam of your telescope has to be turned on, and then you furthermore have to look through your data for a specific FRB hunting algorithm in order to find it. And these three things are rarely true at the same time, hence our very low detection rate. So what we needed was a paradigm shift. Progress in the last few years, or the last few decades in radio astronomy, has meant building bigger and bigger telescopes so you can get better and better angular resolution. But you look at smaller and smaller sections of the sky. And so we decided to do something very, very different. A Canadian team called CHIME, which stands for the Canadian Hydrogen Intensity Mapping Experiment, developed a radically new kind of telescope. So instead of having a big dish and only one antenna, we have four parabolically, oh, you can't really see them on the slides, okay? The point is that you have four sort of half-pipe parabolic cylinders in a row. And there are detectors along the focal points of the parabolic cylinders, such that we have 256 detectors in this direction and 4 in this direction. So we have the equivalent of 1,000 giant telescopes of this size. So because we have 1,000 giant telescopes all built in one, CHIME is one of the most statistically powerful radio telescopes ever built. So to provide slightly more context for how conventional radio telescopes work, normally what happens is that if you have a source that is very, very far away in outer space, by the time the rays from that source get to Earth, they're almost parallel. And because of that, we can use a parabolic dish to focus the rays. If you have a source that's close by, for example, the sun, the rays aren't parallel by the time they get to Earth, so they would kind of scatter around the dish and you wouldn't actually be able to see them. And so that's how we're able to focus so well with these big dishes. So instead of having one dish that looks like this, we have a bunch of detectors that are in these parabolic cylinders. So you might think, well, how do you actually focus if you don't really have a parabola? And this is where the software engineering comes in. So instead of building a physical dish, why not make a software dish, where you simulate tilting your telescope around just by applying timing delays to the signals that come in. So imagine that I wanted to look in this direction. Well, I tilt my dish like this, and so signals would arrive closer or faster here than they would here. And so you can just code that into your software. You have all of your data, just apply delays to this part instead of this part. And if you can do it for one angle, you can do it for any other angle. So that's how we're able to get 1,000 telescopes for the price of just one. So what's the problem with this scheme? Well, instead of having a really big telescope, we now have a bunch of software problems. So to be a little more specific, this is a slide that I borrowed from one of my advisor's talks I think a couple of years ago. But on the left, you can see I've listed a bunch, or on your right, you can see I've listed a bunch of telescopes, and I have the collecting area, the number of beams that they can form, and then the mapping speed. And the mapping speed is what really gives you how powerful a telescope is. So just to give you some reference, FAST is, I believe, the most expensive telescope ever built, $180 million US. It was built in China. Very, very big, 500 meters, quite large. In contrast, CHIME was only $13 million US. And yet you can see over here, CHIME is just as powerful as FAST is. Okay, so does that mean that CHIME is just fast, but for much less money? Well, it's not quite right. CHIME is fast, plus a whole ton of computational problems. To be more specific, our telescope, because there's 1,000 telescopes in one, collects a huge amount of data. So actually, our telescope collects more than a terabyte of data every second. And for those of you who don't know, a terabyte is around 2 laptops worth. So we're collecting 2 laptops of data every second. We will very quickly run out of money and also space left on Earth if we actually collect all of our data and throw it out to disk. And so what resulted was a whole bunch of computational challenges. We needed to really optimize our code so that we could do all of our data processing in real time so that we could find all of these FRBs. And the result requires some pretty fancy computer science. So it originally started as an astronomy project, became a collaboration between electrical engineers, computer scientists, physicists, mathematicians, and also plumbers. It turns out that the computers need to be cooled using water, and physicists are not very good at doing plumbing by themselves. We tried to do it, and it didn't really work, so we hired someone else. So to give you an idea for the kinds of things that we worked on over the past few years to get this telescope up and running, I'm going to tell you about something that I spent about 3 or 4 weeks on. This is a picture of the system. So we have actually 4 different supercomputers for this telescope. We have one that first takes all of the signals and digitizes them. We have another one that correlates them and does all of the beam forming, and then we have the last one that actually detects the fast radio bursts. And you can see them because they are in literal shipping containers next to the telescope. This is the telescope, and you can see there are 3 shipping containers off to the side. Those are all of our hand-built supercomputers. A lot of sad graduate students spent a long time doing that. All right, so what does this data actually look like? The data that we collect from the telescope raw looks something like this. I don't know if you can see anything in this, but I'm telling you there's a pulsar. I definitely can't see one. It is very noisy. And this is because of all of these newfangled technologies, cell phones, televisions, messing up with our data. Actually, that band at the very top, that's the LTE cell phone band. So your cell phones are annoying astrophysicists. But the point is that our data is extremely messy, and there's also a lot of it. So we have to clean all of that in real time and then analyze it for signals, also in real time. And the result is a very complicated software pipeline that takes stuff that looks like this and makes it at the end look like that at the top. And I know it's kind of hard to see on the slide, but you'll see if you look closely, there are dots, right? Those are the dots of a pulsar that it actually found in this data. Okay, so the point is that to get from these bottom 2 slides, which show data as frequency as a function of time, you need to the top slide, which gives you dispersion measure as a function of time, that is how curved the paths are that these pulsars take. You need to do some pretty fancy algorithms. So my advisor wrote an algorithm that actually sums over all of the possible tracks that a pulsar could take, and that's what the top plot shows. And so that's the only plot where you can actually see the pulsar. Even in the cleaned frequency data, you still can't see the pulsar. So that's why this cleaning is so important. But if you look at the bottommost plot, you'll see that there are a lot of parts where the data has been just completely blacked out. And if I had fed this directly into the algorithm that does the summing that I talked about, we would have gotten false positives all over the place. The algorithm does not handle blacked out data very well. And the problem with false positives is that we collect so much data that if we actually started to write all of these false positives to disk, we would again quickly run out of storage space. So one of the tasks that I was given that just lasted a couple of weeks was to find a way to sort of fill in the data, make it very smooth. And a sort of sensible way of doing this would be to add some noise to the data. But not bad noise, right? Because originally this is what noise looks like. We want to add a very particular kind of controlled noise called Gaussian random noise. And Gaussian random noise is parameterized. All it's parameterized by is a mean and a variance. So if you know the mean and the variance of your data, you can just fill in with noise that looks very similar to your data. And so that was what my task was, and that's how you get from this bottom slide to the top one, which still has a lot of blacked out portions, but is at least a little bit cleaner. So the way that you do that is by keeping a per frequency variance estimate running, and you already know the mean because of some science. And so the next step, once you have this variance information, is to actually fill it in with noise. But it turns out that this Gaussian random noise, this fancy noise, is a little bit hard to generate. In fact, my advisor and I did a little bit of a back-of-the-envelope calculation, and we realized that if I was to do it using existing algorithms, it would consume about half of our total supercomputer time. So that would not be good. This is supposed to be a very small part of our pipeline. And so what followed was a month-long rabbit hole of black magic code optimizations that I had to do in order to make this work. So the trick ultimately came down to something kind of odd. And that was that it turns out that it's very easy to generate uniform random numbers. And what I was able to do is, using a bunch of uniform random numbers, I was able to simulate this much more complicated Gaussian random noise. So the way that works is using a really nice theorem called the central limit theorem. I promise this is the most technical this talk is going to get. So the central limit theorem is a beautiful, beautiful theorem. What it states, very formally, is that given any random variable with any distribution, if you repeatedly convolve this random variable with itself, eventually in the limit of infinite convolution, you get back a Gaussian. Now I realize that sounds kind of complicated, but it's actually very straightforward. A random variable is any variable that can take on a set of values with a particular probability. So let's imagine you have a dice, or a die. That's the simplest example. There are 6 different possibilities it can have, and each one is roughly equally likely. And then when you roll it, it takes on a particular value, right? So we can plot the probability distribution for a die, and I've done that in the top right corner. So you can see that there are 6 different possible values, and each of them is equally likely, right? Those are what the bars represent. Now, instead of just rolling 1, let's roll 2. If I roll 2, then the probability distribution looks like what's in the top, in the middle there. So it's more likely that you'll get something closer to 6 than you will 2 or 12, right? And if you just repeatedly do this, you roll more and more and more, eventually there's a theorem that says that you're guaranteed to get a beautiful bell curve at the end. And so you can see that plotted over here. There's 256 rolls, and you can see you get a beautiful bell curve. So this was the trick. You start out with uniform random numbers, and then repeatedly average them together until you get the Gaussian that you want. So what followed was I wanted to check if this works, of course. So I wrote this type of filter, which generated this random noise in Python, which it did work. Then I rewrote all of this code in very optimized C++, a very complicated low-level programming language. Still was too slow. So eventually I ended up writing it in x84, vectorized 256-bit Intel assembly language kernel. So that is literally telling the computer, okay, you have this register, add it to this register, then commute the bits around. So I had to spend all of this time writing this incredibly low-level code just to simulate random numbers. So this was the kind of process that went on for about 5 years in developing this telescope. We'd start with an extremely simple problem, just making our data smoother. And it takes weeks and weeks and weeks to go down this optimization rabbit hole. Okay, I told you that I was done with technical stuff. I promise I'm done with technical stuff. So I have some very exciting news, which is that finally, after all of this work, we actually started running the telescope almost full-time a few months ago. And we actually published our very first science results at the start of this year in Nature, which was super exciting. We detected a total of 13 new fast radio bursts, including a very, very fancy one, a 14th one, that actually repeated. So, as I said before, we only had 2 dozen or so total event detections, and this was from around a week or 2 of engineering debug data. So the future is very, very promising for our telescope, and sort of off the record, we have many, many more event detections, which is very exciting. We're holding on to them for now. But we really hope that because of all of these algorithmic challenges, we'll be able to throw data at this problem, which is something that we've never been able to do before. And maybe if we have enough data, we can finally start ruling out these alien theories, right? So thank you very much. If you have any questions, feel free to ask.
Hi, Maya. That was great. Can you talk about the location of the giant telescope and why that's a great location, please?
Yeah, so it's in Tickton, BC, which I had never heard of before, but apparently there's a lot of wine there. Yeah. So in addition to being home to a lot of wine, it is also home to DRAO, which is a big radio astronomy park. So there are actually a few different radio telescopes in the area. I actually don't know too much about why it was selected. I mean, it probably has something to do, of course, in BC, higher altitude, so better viewing, but other than that, I don't really know. But what's really exciting about this is it's actually the first major Canadian telescope in the last 50 years. So we're really trying to prove to the government that they're going to get their bang for their buck.
So, how many times in your life have you actually said, I don't know?
I don't know.
Far more often than you would think. Really, it's like that. I don't know most things. I feel like the more and more science you know, the more you realize that you don't know, right? And so this year, I worked on this project last year. I'm still doing a little bit of work on it. But this year, I started doing some really crazy stuff in very theoretical physics on have no idea what I did all summer.
Does all the smoke from the forest fires affect your work?
So the great thing about radio astronomy is that the answer is actually no. What's really nice is that if there are clouds in the sky, does not matter. So with visual, if we do optical astronomy, of course, smoke, clouds, all those sorts of things would make a huge difference. But with radio astronomy, the difference between radio waves and light waves, right, is just a matter of wavelength. They're the exact same thing. Light and the signals that make your radios work, same thing. It's just the energy or the wavelength are different. And so because radio waves are such long wavelength signals, so I think it's on the order of centimeters to hundreds of meters, it doesn't actually matter if there are small little particles in the way because the wave just can keep propagating because the wavelength is so long. So luckily, no.
Okay, I'm going to ask my question. I'll pass the mic on after. First off, thank you so much. That was fascinating. I'm going to take the fan of the alien theory approach to my question. What I found interesting when they came out with the article, and it made some Twitter and all kinds of fun noise if you're a fan of astronomy, is the fact that I think one of the verses regular frequency or something.
Yes.
And so that's perhaps feeding the theory that it's not natural, right? The fact that it's regular. So what are your thoughts?
Yeah, so I kind of glossed over this, but there are two classes of signals. So I mentioned these are sort of random bursts, and they truly are. So sometimes there'll just be a burst, and then nothing else will happen. And it's totally random when they do happen. But there is one burst that people had previously observed that would occasionally repeat. And when I say repeat, I don't mean like a pulsar where pulsars are like clockwork. They go and they go and they go. This would be like completely random. And so that was part of what fed into this alien theory, right? What was exciting about this top paper is that we actually discovered a second one of these kind of repeating bursts. And so now it looks like there are kind of two classes of signal. One that repeats, but not periodically, just completely random. And then one where it's just a one-off thing. And so that was really interesting because when we had just had these one-off signals, we thought maybe it was some sort of cataclysmic event, like a neutron star falls into a black hole. But clearly, if it's repeating, that can't be the case. And really, we don't know. I mean, there are so many theories out there. Some of them rely on crazy things like string theory, right? And so that's why this research is really so exciting, because if we can figure out, oh, it's the string theory, then that will tell us a lot about whether or not string theory is true. So.
Maybe you just answered it. Is there a practical application for what you're doing?
So this isn't a question that I ask myself very often, but there are some practical applications. So I mentioned very, very briefly that maybe we can use these to probe the universe like we did with supernovas and pulsars. And the idea with that is that we hope that we might be able to, so with pulsars, we were able, because they're so regular and they repeat so nicely, we can do lots of things with them. So an example is that people are currently trying to look for gravity waves by timing the pulsars really accurately and noting some timing delays in pulsars. People use supernovas to figure out how far away things are. And so it's our hope that we might be able to use fast radio bursts for a similar thing. Because they are so distributed throughout the universe, if you notice something about signals over here are more dispersed than signals over here, that tells you that there's more stuff between you and the fast radio burst than over here. So we hope that all the time with these kinds of radio transient signals, we hope that we can do some sort of mapping, figure out if there's matter between us and the fast radio burst, those kinds of things.
Place to go when we learn this world.
Maybe.
I just have a question. You say they're fast radio bursts, but you describe this as high amplitude radio bursts. Why are they fast?
They're fast because of the duration of the pulses. So, let's see, can I go back to the first one? The fast part is the thickness of the burst. So you can see over here, this pulse is very, very thin. And that's the fast part. It's only a few milliseconds in duration. So the amplitude, the energy is extremely high, but it only happens for a very short amount of time. And that's the fast part.
And how do you know how far away they are? Because you need to know that to say it's really powerful.
So that's part of the problem. I mean, we have very, very large error bars on how far away these things are. And the reason is that normally what we would do is if we notice there's a pulsar somewhere and it's pulsing repeatedly, we can measure it with two telescopes that are really far away and use something kind of like parallax to figure out where it is. But here, because the bursts are so short, we don't even have time to tell a telescope on the other side of the world, hey, go look at this, because by the time you tell And so because of that, we have very large, so it's just up to the telescope, a single telescope to be able to localize it, which it can usually only do pretty poorly, like at around 5 arcseconds localization. So it's pretty bad. But we do know that it is extragalactic, and the reason we know this is because of the dispersion measure. That is how curved the pulses are. So if the pulses are very, very curved, that tells us that there's a lot of stuff between us and the host. And if it's curved enough, we know that there's enough stuff between our galaxy and another galaxy in order for this event to happen. So if it was like a short kind of thing, you could say, oh, maybe it's within our own